Welcome back, guys. We're going to talk about, in this video, what is an acid, right? That's the question. How are we going to define an acid? Because we want to define this. I want to be very clear. So the first definition, Chem 1, almost every Chem 1 book, comes up with Savante Arrhenius's, the Arrhenius acid. All right? And that acid, it produces hydronium in solution. Now, a little note here, all right? Note, solution / water. So note, hydronium is basically the same thing as H+. So we're going to treat it the same way, okay? Because the proton is going to hydrogen bond to water. Or bond to water. It's the same thing for us. It can get more complicated than that, but that's where we're going to leave it in this one. All right? So, for example, an acid like hydroiodic acid, right? That in water produces our H+, and then it has I-. That would be an Arrhenius acid. What about an Arrhenius base? Well, that produces hydroxide in water. Well, what would that be? Like your potassium hydroxide. In water, we get potassium ion and hydroxide. So there's the Arrhenius definition of an acid base. And that's a great definition. It works really well for most of what we do in Chem 1. But it's not complete. And we're going to talk about the next definition by Bronsted and Lowry. I think the O on Bronsted technically has that. I don't even know what that's called. That's what it has. And this is probably the most important system of acids and bases for aqueous reactions. All right. So the acid is an H+ or proton donor. And the base is an H+ or proton acceptor. All right, so the donors accept the proton. The donors are the acids. Donate the proton's acid. Accept the proton is the base. All right. So what do we mean by that? If I had hydrofluoric acid and water, well, what would be on the other side? What are your options for the other side? All right. Well, if hydrofluoric acid is the acid, by definition, it's going to donate the H+, right? So right here would be the species coming off, the H+. There's the H+ going over. That means water would be the base. On the other side of the arrow, we would have our hydronium that was made, and then just F-, fluoride. Now, this reaction can go both ways, right? This H comes over, goes to hydronium, so now we have hydronium and fluoride. Works out great. Well, if we look at the reaction going this way, so we put our I over here, right? This H, one of these H's can come back to fluorine. That kind of makes sense, doesn't it? So that means this could be a base. Or excuse me, this could be an acid. Water could be, or hydronium is an acid, right? And fluoride would be the base. And they're the conjugate. So this would be the conjugate acid and the conjugate base. What do we mean? So these are our acid-base conjugate pairs. Our base and our acid, right? And so look at it as where the proton is. So if we look at the reactant side, acid, because we have the proton, base, we don't have the proton. If we look at the product side, base, no proton, acid has the proton. So all we're doing is you're taking this H plus and it's going back and forth. H plus, back and forth, right? So if you have the proton, you're the acid. If you don't have the proton, you're the base. It's kind of like if you're playing catch with a baseball or softball, or you're playing catch with a football, or you're passing with a soccer ball, whatever, or basketball, whatever it is you have. If you have the ball, you're the acid. If you're waiting for the ball, you're the base. All right. Now I like baseball as an example because or softball, it doesn't matter. The pitcher would be the pitcher, right? So it doesn't matter which one, baseball or softball. The pitcher is the one that primarily throws the ball, right? They're the main thrower of the ball. However, the catcher has to throw the ball back every time, right? And so when the pitcher has the ball, the pitcher is the acid and the catcher is the base, right? But once the pitcher throws the pitch, and let's say the batter doesn't hit it, and the catcher catches the ball, now the catcher is the acid, all right? We don't want to start the play with the catcher being, with the ball, so the catcher throws the ball back, all right? But that's a good analogy of acid base, right? Who's the acid, who's the base? And so depends on it. If you're looking at, I didn't want to do that. If you're looking at this side, all right, acid and base. If we're looking at the product side, acid base, right? They're conjugate pairs. All right. Okay. Another example. You have ammonia plus water. Well, what can happen here? Well, we know ammonia would be a base. Why do we know that? And maybe I should draw the Lewis structures of these things, right? Because ammonia, let's do it a little neater. NH has that lone pair right there, right? Or water, there we go. So water is going to be the acid. All right? Because one of these H's, doesn't matter which one, they're symmetrical, is going to find its way to that lone pair. Right? So on the product side, you're going to get ammonium and hydroxide. Okay. So if ammonia is the base, that means ammonium would be the conjugate acid, because now it has the proton. And hydroxide would be the conjugate base. And so if we look at our conjugate acid-base pairs, there's our acid, there's our base. All right. Now you might have noticed something. I said water's a base there. Water's an acid there. It's kind of neat. What's going on here? Well, water is an example of amphoteric. Right? Which means it can act as an acid or a base. Right, so water can be either one. It can be an acid or a base. Again, it's a behavior thing. All right. So this Bronsted-Lowry acids and bases, you got proton donor, proton acceptor. Right. So in order to be an acid, you have to have a proton to donate. In order to be a base, you have to have a space to accept the proton, usually a lone pair. All right. Hopefully that makes sense. And we'll see you in the next one, guys. Take care.